Hi, I'm Elizabeth with Logic Walk, and welcome to Chapter 3. In this chapter, we're diving deeper into another I/O device you're all very familiar with, the keyboard. When a computer and a keyboard are connected, pressing a key alerts the computer, which then performs an action, like printing the character on the screen or moving a player in a video game. Today, we'll explore what happens behind the scenes when you interact with a keyboard. Our Logic Walk simulator looks a bit different this time. Just as before, we have instructions, memory cells, and a program counter. Now, we also have a new section called the interrupt table. Together, these elements form our computer, which we'll call Computer A. At the bottom of the simulator, you'll see the keyboard, which we'll refer to as Keyboard A. When a keyboard is connected to the computer in the simulator, the keyboard gets access to memory cell 8 and interrupt cell 0 of the computer. When you press a key, the computer stores its corresponding ASCII value in memory cell 8. Then, the keyboard interrupts the computer by storing a 1 in interrupt cell 0. This interrupt forces the computer to jump to the instruction associated with that interrupt. Let's go over the program we're about to run. Instruction 0 tells the computer to wait. Instruction 1 tells the computer to add 1 to memory cell 9. This helps us keep track of how many times a key has been pressed. Instruction 2 tells the computer to jump to the address stored in memory cell 4. We'll talk more about this value later. Now let's take a quick look at the interrupt table. In this lesson, we're focusing only on the first row, row 0, which is triggered by the keyboard. The second column displays the interrupt value, and the third column shows the instruction that the computer executes when it's interrupted. Before we run the program, let's consider a real-world example. Imagine you're washing dishes and you hear a knock at the door. Since you're expecting a package, you pause your dishwashing, open the door to receive the package, and then return to your chores once the interruption is over. This is exactly what happens with the computer. From this point on, we're going to run the computer continuously instead of stopping after each step. When an I/O device interrupts it, the computer stops its current task to perform the required action, then resumes exactly where it left off. Let's run the program and see what happens. Right now, the only change that you'll notice is that time is advancing, which means the computer is running. Nothing else appears to be happening because the computer is at instruction 0, waiting for an interrupt. Next, I'm going to press a key. If you're following along in the simulator, the exact moment that you press a key might differ from mine. That's completely normal. Interrupts can occur at any time while a computer is running. Let's see what happens when I press E. After I press E, the corresponding ASCII value for E is stored in memory cell 8. However, several other things happen very quickly, so let's slow it down and break it down step by step. When the computer is interrupted, the keyboard places a 1 in interrupt cell 0. I'd like to note that for interrupt cells, 0 means off or false, and 1 means on or true. So when the keyboard places a 1 in interrupt cell 0, that cell is considered true or on. When the interrupt cell is turned on, this alerts the computer that it needs to execute the instruction associated with this interrupt as defined in the interrupt table. Next, the computer saves the current PC value in memory cell 4. Doing this ensures it knows where to return once the interrupt is handled. Next, the computer executes instruction 1, and memory cell 9 increases by 1 to keep track of the key press. And finally, the computer moves to instruction 2, which tells it to jump back to the address stored in memory cell 4. In this case, back to instruction 0, where it will wait for the next interrupt. I'd also like to add, if you continue pressing keys, you'll notice that the value in memory cell 9 increases by 1 each time, which is just the computer keeping track of how many keys were pressed. Now that we've broken down the interaction between the keyboard and the computer, let's take a closer look at how the simulator's state changes during this process. That concludes our overview for this lesson. Let's dive in and explore these interactions in more detail.